Jan Rhomberg-Kauert. Sorry for your pronunciation. Also from Vienna University of Technology, Austria. And I will share.
Can everyone hear me?
Yes, good. Right. I will share my screen, and here's your presentation. Not yet. Yes. Now.
Okay, perfect. Hello, everyone. My name is Jan Rhomberg-Kauert. I'm also at TU Wien, and today I'm presenting my research on whitewater LiDAR. This has become a topic in the University of Innsbruck, which came to us with a problem. Basically, can we map water bottom returns in whitewater rapids? And the general consensus is no. So we sent out to develop a method that can. So what is whitewater rapids? You can see on the right these turbulent waters, and basically there's a lot of air in there, and with green lasers we cannot really penetrate it, or at least that was the assumption. So we did a lot of in situ measurements where we measured ground truth data with pole measurements. As you can see me standing there here in the block ramp at Pilaf River. And you can see it's quite hazardous, so this is not really something one wants to do, which is why we want to apply LiDAR to exactly these type of rivers. And in particular, we want to apply full waveform bathymetric LiDAR to our different study sites. So basically, we record not only the peak, but the whole return. In the end, we have 3 study sites. We have the Pilaf River with this block ramp, which you've seen before, and then we have 2 mountain rivers. Basically, Pilaf River is a bit more calmer with just this one rapid, which is artificially built. And then you have the mountain rivers, which have large boulders and the typical flows that come with those. You can see there in the orthophotos. For the Pilaf data, we have normal returns in the calmer part, which you can see on the upper part, where you get the bottom nicely mapped out, and we have 2 returns in the water column backscattering, and a LiDAR waveform. And then we have the rapids, the second part, where the waveform looks really fuzzy and basically see the reference data, but not really any return the LiDAR data. Similarly, in the mountain river data, the waveforms again look really fuzzy and there's a lot going on. But if we look, especially in the higher lit part in the cross sections on the left, you can see that there are gaps in the data or data completely missing because of the white water. So now we want to take these waveforms, which you have seen, and extract the bottom echoes from these waveforms, because there is still some energy not attributed to the water column backscattering in those waveforms. And from that, we can extract new points. And basically, the method splits into 2 parts, which we're going to see in a second. We're going to see combined waveform analysis. We look at general trends, basically combining multiple waveforms of spatial proximity into a higher resolution one to look at general trends. And then we're going to analyze single point waveforms. We can extract new bottom returns and basically fill our gaps. The averaging basically takes waveforms of close spatial proximity. As you can see here for the Pilaf River, for the standard gravel bed river part. And then we interpolate across the averages of each of those samples and get a really nice waveform that attributes to those water column backscattering and then the return. And later on, we will see that this looks a bit different for the white water. And similarly, or on the other hand, for the white water point extraction, we fit the Gaussian pulse convoluted with an exponential decay function to the echo recorded and then look at the difference that we call the residual. And basically, when we analyze this residual, there are 2 different options that we can look at, or results we have seen later on. We have high amplitude waveforms where this convolution fits really well to the recorded waveform, as seen on the left illustration. But then we also have low amplitude waveforms, as seen on the right illustration, where we have a difference between the residual so basically like the recorded waveform to the fitting, and that we can analyze. And now going to the results, we have the recorded waveforms average, and as you can see here already for the block ramp, high amplitude waveform, it fits quite well, but for the low amplitude waveforms, we see there is a residual and there's something left in remaining energy in this average waveform. So we want to analyze these peaks, but first we look at the standard waveform again for the Pilaf River to give you a bit of an overview if you're not as familiar with full waveform LiDAR as I might be. So there, basically the fitting fits quite well to this exponential decay or the water column backscattering of the first part, and then you have the peak, which of course in the white water we don't. But as you can see here, for the mountain rivers, especially I want to draw your attention to the panels on the right. There we have the low amplitude waveforms, and there you can see in black the convolution fitted to these average waveforms, and then the dotted line is the residual. As you can see here, especially for the Fischbach River, there's a second peak to be detected. Now, if we want to look at points, basically why we want to do this, on the left, we can see a digital terrain model gathered from 8 hours of in situ measurements in the block ramp. On the right, you can see a single flight strip of LiDAR with the new data applied. So basically, before we had no points at all, and besides reference, and now we can fill those gaps. Similarly, for the mountain rivers, you can see the reference data, you can see this gap in the data where we have white water, and we can fill in that gap quite nicely. We do some clustering outliers to remove points that are wrongfully assigned on the side because we have really dense section in the white water. As you can see here, it matches overall quite well the reference data. And similarly for the Fischbach, we had barely any points below the water surface. You can see now that we get a nice bottom profile through exactly these white water point extractions. And basically this gap closes or overcomes the challenge of applying white water, bathymetric light to white water. And you can see also in the quantitative evaluation that if we compare the reference data to the new points versus the old points, so before we had more than 50 centimeters deviation because we partially had no points, and afterwards we have mostly less than 20 centimeters deviation. So it's still overall quite noisy, but we closed the gap. And again, as outlined in the introduction of the results, the left panel, panel A, took 8 hours of in situ measurements and was pretty dangerous according to colleagues at Innsbruck. And panel B is single flight strip, so 30 seconds of data gathering and then another 15 of processing. And here we can see, we saw in panel C there, the differences between those, and we can see the shift of deviation. So before we had no points underneath the white water leading to high deviations. And now basically it matches really, really well, just with a higher degree of noise than usually expected. So with this, I thank you very much for your attention. And if any questions, I'm happy to answer them.
Thank you, Jan. Very specific topic for you. And it's quite dangerous to acquire the data for you.